every other element, then first you're going to get to the end and then it's just going to repeat. And then this is how you can formalize it. So first you write the definition of Z mod P being like generated with this generator element, which for us was 2. So you just raise it to all the powers up until P minus 2. Then you can square everything. So you're just multiplying everything by 2 in the exponent. And then you see that basically the second half is the same as the first half. So you can just shorten the list and only like consider every other element. And this is due to something called Fermat's little theorem, where basically a to the p is congruent to a modulo p. So that means that there's like a cycle. And if you would basically take, since this is like g to the p minus, or g to the p plus 1, so you can replace g to the p with just g. So that means that you have g times g, which is the same as g squared. And so that's basically how you go from the second row to the third row. All right, we got another thing to look at. This is called the Jacobi symbol. So it's basically defined to be positive 1 if the input is a quadratic residue modulo p, and negative 1 if it's not a quadratic residue. And it allows you to check, just whether a number is a quadratic residue or not. So,
I learned it, but then also I was always thinking it's pretty useless.
we're gonna find some uses for it.
Okay, great.
Okay. So we've got p is greater than 2, so it's an odd prime. And then we have this definition of the Jacobi symbol. So we can basically prove it in both directions. So first, you suppose that, Well, first we can look at the generator, since we know that Z mod P can be generated by some number. So we can just write everything in terms of this G. So let G be the generator. Of Z mod P star.
Okay. So just to repeat, generator is a thing that you plug in the powers and it gives you the cycle. Okay, good.
So it's just a number in Z mod P star where you can raise it to all the powers and you'll get every other element that you need. It's very useful. If X is a quadratic residue, mod P, then we also have X is congruent to G to the power of I for some I, where I is an even integer, since we know that X has a square root because it's a quadratic residue. Since I is even, that means that I can be written as 2 times j, where j is an integer. So this z just means it's a number, like a number that can be positive or negative or 0. So that means that x to the p minus 1 over 2 is the same just by doing this substitution. So 2j for I, and then g to the I for x. So you have x is equal to g to the 2j. And then this thing would then be equal to g to the 2j p minus 1 divided by 2. And then you just, so you can cancel the 2, so you get g to the p minus 1 times j, which is equal to, so by that Fermat's-little theorem that we had before, basically just that, well, we can go back. What was it? Yeah, so a to the p is congruent to a. So that means that a, or g for this case, to the p minus 1 is congruent to 1. And then, so that means that we have this whole thing is equal to 1 to the j, which is just the same as 1 mod p.
Are there any questions to this point? Just to make sure. Do you want us to like...
I still don't understand what is G. Why you can use G to...
So yeah, basically, if you have any prime number, you can use G, or find some G within the modulus